Welcome to the course on statistical mechanics of phases and phase transitions. We are discussing the transverse field Ising model in this chapter on quantum models. And in the last lecture, we showed that the transverse field Ising model, which is given the short name TFIM, can be mapped to a fermion problem. And we were motivated to do this by realizing that the ferromagnetic state can be thought of as a condensate of X-flip excitations. We used the idea to convert the transverse field Ising model to a problem of indistinguishable quantum properties. Although we can pose that as a problem of hardcore bosons, it does not help us find the solution. So, to achieve using techniques of fermion problems to solve such ground state problems of many particles, we transform the problem to a fermionic description, and this is what we call the Jordan-Wigner transformation. And the Jordan-Wigner transformation is a non-local transformation between qubits defined on sites to fermions defined on sites. So, qubits defined on sites, they do not transform to just directly to the fermions defined on sites, they will also look at the qubit state, the full qubit state of the system in making that transformation. Okay. So, we obtained a fermionic model associated with the transverse field Ising model. What we are going to do in this lecture is we are going to find the ground state of the transverse field Ising model in the fermionic language. Once we get the ground state, we will then switch back our discussion to our transverse field Ising model language, and we will explore what physics it contains. Okay, let us quickly recap what was the mapping. So, we first converted the transverse field Ising model to a convenient basis. So, the Ising interaction term is now written in terms of the X operators on qubits, and the transverse field term is written in the Z using Z operators. Now, if you observe that X is sigma plus and sigma minus, and observe that sigma plus sigma minus sigma plus is the identity, and the fact that this quantity commute whenever I not equal to j, you will see that this transverse field Ising model is simply as a restatement or in some notation a hard-code boson model. So, the transverse field Ising model can be viewed as a hardcore boson model. But what we decided to do was we wanted to take this description instead of hardcore bosons to fermions. So, for this we map the upspin state at site I to the vacuum at site I, there is an I missing here and also here. So, you will see that we mapped these states, this is what we want to imagine, and to get this mapping done correctly, as we saw in the last lecture, we had to take care of the string of fermions that are that show up to give you the correct sign of the creation and annihilation operator, and ensure that the hardcore boson algebra of the sigma operators is satisfied even if you start with these fermionic operators. So, the dictionary is this. So, whenever I see sigma plus, I need to replace it by this, and whenever I see z, I should replace by 1 minus ni, when I see xi, I should replace it by this. This is a dictionary. I take this thing and put it into this expression, and you will see that in this process of mapping Hamiltonian to Hamiltonian, etc., let us also revise what happens to the symmetry. So, in this basis where we have chosen here and written the transverse field using the Z operators of the qubits, the global Z2 flip, right, the flip symmetry of the transverse field Ising model is described by the product of all the Z operators. So using this mapping that Zi goes to 1 minus 2 Ni, and remembering that 1 minus 2 Ni is same as e to the minus I pi times Ni, you will see that this object turns out to be the parity operator. So the fermion operator in the the flip operator on the qubit side maps to the parity operator on the fermion side. So now if I take the results that I had on the previous slide and put it into this Hamiltonian, I will see that this Hamiltonian in the qubit language will transform to this Hamiltonian in the fermion language. So there are very important things we should remember. This mapping holds only in the qubit flip singlet sector. So you have to work in the states of the qubit Hilbert space where the flip operator acts as identity. Remember, this is exactly the sector of the Hilbert space where the duality was holding. And this implies even parity of fermions. Right? So this is the statement. So we are going to work in the sector of the fermionic Hilbert space with even parity, and corresponding sector in the qubit world is the flip value should be 1. The flip should act on the state as if it's identity. Okay. Now the fermion problem also has another important condition. It has anti-periodic boundary conditions, right? So that is equal to this, and that is why you see up until here this minus sign is there and it becomes plus here, and that is because of these anti-periodic boundary conditions. Now, if you have studied condensed matter physics, you will realize that this Hamiltonian, which is Hamiltonian of fermions, has terms of the kind C dagger, C dagger. So there is a term. So for example, if I multiply this out, you will see that there is a term of the kind C dagger I plus 1 Ci, C dagger I. This term is what is typically called a pairing term. So it creates like a pair of fermions on neighboring sides. So this kind of models describe superconductors. So if you write out a theory with this kind of thing, it's typically called a BCS Hamiltonian after the BCS theory of superconductivity. And what we have to do is we have to treat, we can bring in techniques from analyzing superconducting states, etc., to analyze this problem. And to impose this condition, C dagger n is equal to minus C0, we write this site operators in terms of momentum operators, which we had discussed in the last lecture. And what we will see is that the allowed values of momenta, if n, the number of sites is chosen to be even, will turn out to be these values of k, right? There are n such values of k, and those are listed out by running from m going from 0 to n minus 1. Okay, and this k is called the crystal momentum, is the momentum in the crystal. Okay, now the question becomes, how do I find the ground state of this Hamiltonian? Okay, so let me walk you through this. So we saw that this is a one-dimensional superconductor. Like I said, you can bring in techniques of analysis of such problems from superconductivity to this problem. So first what I do is, I transform this problem into a problem written in terms of the momentum basis operators, namely C dagger k and Ck. So I invite you to do this. You can just substitute the Fourier transform that I mentioned in the last slide into this expression and go through the algebra. You will realize that it will land up into this form. All the operators here are now written in momentum space. The k quantum number is the crystal momentum, and crystal momentum runs over all the values that I had listed in the last slide, which respect periodic, anti-periodic boundary conditions. Okay. And this is the main thing that I mentioned when I said that you can bring in ideas from superconductivity to the analysis of this. So this way of taking a model like something written like this into a form where there are these two components, it's like some kind of spinner kind of state, where there is something here and it's a two-component object. This is a very very standard thing in the theory of superconductivity. So here what I have done is I have manipulated this expression to make it look like this. So I have organized for at every k crystal momentum, there is a matrix of operators called Ck and C dagger minus k. So what this can do is it has a piece where I destroy a fermion with momentum k, and there is another piece where I create a fermion with negative k. So you see, destroying a fermion with negative, so you start from any state, you destroy a fermion of positive k, or you create a fermion with negative k, the total momentum is still, the change in momentum is still minus k. That is why you are able to combine these two. Okay, and you rewrite this. Now first you have to observe is that this is a matrix which is a Hermitian matrix, and it has some nice properties. If you look at it, you will see that the trace of this matrix is 0. Okay, and all these exponentials etc. have given rise to these cos and sines once we have rearranged it in this form. And the coupling constants of our original transverse field Ising model, which are J and H, they show up in the matrix. Okay. So if you are so minded, you might want to pause the video and work out this algebra, or you could work this out later and you can follow along, and you can see what are the interesting physical consequences that will come out of solving this. Okay. So what is involved in finding the fermionic ground state? So the first thing is, we see that momentum is a good quantum number because we have not broken any translational symmetry. So we can focus on a particular momentum and diagonalize the Hamiltonian there, and that is what I have done here. So what I do is I write Hk, and this is the matrix of eigenvectors, is U times the matrix of eigenvalues. Now remember, I pointed out that the trace of the matrix is 0. This means that the eigenvalues have to sum to 0, and it is a Hermitian matrix, therefore eigenvalues are real. So associated with every k, I will have a real eigenvalue and positive because it is summing to 0. One of them is positive and the other is negative, and they are real. Since they are real, one of them is positive and one of them is negative, and of equal magnitude. And you will be able to show very simple exercise that E of k, the positive energetic eigenvalue, is the square root of this quantity. Okay, it depends on our J, H and the cosine value of the crystal momentum. And what are the eigenvectors? Again, it is a very straightforward exercise to do this. You can find the eigenvectors are this, they are orthonormal, and all the good things that happen with Hermitian matrices. And so everything is expressed in terms of some angle theta k, which is actually a ratio of J sin k by H minus J cos k. Okay. Now the way this proceeds is to use this Uk to transform your original fermions, which were Ck and C dagger minus k, to a set of new fermions. These are called gamma k and gamma dagger minus k. So there's only one fermions, strictly speaking, gamma k. This is just like its partner, if you wish, right? These are called Bogoliubov quasiparticles of the superconductor. Okay. Now I insisted that these are fermions, right? That means they must satisfy the fermionic algebra, and I invite you to check that all this transformation will enforce the will respect the fermionic algebra. In other words, if Ck's are fermions, then gamma k's are also fermions. Okay. So I have managed to diagonalize this Hamiltonian, and I have managed to write the Hamiltonian in terms of these new Bogoliubov particles. Okay. Now a bit of algebra will tell you that this is just counting the number of Bogoliubov particles in the state K minus this quantity, and you can just use the fermionic anti-commutation relationship and observe that summing over minus K is same as summing over K, and all the nice details such as E minus K is E plus K and all of that. You will be able to see that the total Hamiltonian is this number which is sum over K Ek, that is these guys, plus twice Ek times gamma dagger K gamma K, which counts, remember n is like C dagger C, same thing. It counts the number of Bogoliubov quasiparticles in the state K. So this operator's eigenvalues either 0 or 1. Okay. So we are now ready to find out the ground state energy of our system. So how do we find out the ground state energy? So I am going to make a statement and I am going to pose a question to you. So the ground state of this system is the vacuum of gamma fermions. That means the statement is that the ground state has no gamma particles, right? This is the statement. So why is that true? Okay, a hint is you look at the fact that energy of E of K is never negative, and a fermionic ground state is set of all occupied non-positive energy states. They will get occupied. That's the statement. So if you take these things together, you will see that there cannot be any gamma fermions, because if I have any gamma fermion, I will have a positive energy state occupied, but that is not what a fermionic ground state is. So the ground state is, since I don't have any fermionic, I don't have any Bogoliubov quasiparticles in the ground state, I can just drop this and the ground state energy is just this quantity. Okay. So the ground state energy is just this quantity, so it's sum over all K E of K. Okay. So now what I can do is I can find the ground state energy density. How do I do this? I sum over all K and I divide it by the number of sites. When I go through this exercise, I can show that the sum over all K will become an integral in the thermodynamic limit, and that's actually quite easy to see. The interval between one K point and the neighboring K point is 1 by 2 pi, right? And so I can write that like something like dk, and then this 1 by 2 pi just shows up, and it's actually I should say that the dk, the difference between neighboring k's, is 2 pi by n. So what I do is I divide by, multiply by, I have a factor of 2 pi by n, and I have a factor of n by 2 pi outside, and 2 pi by n I call dk, and I run n going to infinity, so that becomes an integral from minus pi to pi. So I will have n by 2 pi here, and I divide that n here, and this just becomes the integral. So hopefully that's clear to you. Okay, so with that I will be able to see that the ground state energy density is this very nice integral here. Okay, we should immediately check whether we have got the correct answer or not in the known limits. So suppose I put h is equal to 0, then you will see that the answer will be square root of j. So that will be j, so integral from that will be 2 pi, and the answer will be minus j is the energy density, which is very nice because I indeed get that answer. And if you put j equal to 0 and look at what is the energy in the other, the paramagnetic side, you will see that the energy is minus h, which is also correct. So to perform the analysis now, it is very natural to define a dimensionless coupling constant. Remember, we always want to see the physics in terms of some dimensionless coupling constants, dimensionless quantities. So here the natural dimensionless coupling constant G is h by j. And if I want to define a dimensionless energy, I just divide it by j. and you will see that E grounds, this ground state energy density divided by J is this quantity, which has a well-known analytical result. This integral is complete elliptical integral of the second kind. You can express it in that form, and therefore you can express the ground state energy by an exact result in the thermodynamic limit, by an exact known function, special function in the thermodynamic limit. Okay. So this is a remarkably beautiful result, which we can derive based on the transformation from qubits to fermions. Okay. So from here on, we have solved the problem. We have got the ground state energy. We are now going to explore what is the physical content of our solution and what does our solution teach us. So we have solved this transverse field Ising model, and we know, I am going back to the TFIM language, as you can see, and I have got the ground state energy solved as this, which I am copying from the previous slide. Okay, now I can simply use any mathematical software and I can try to plot what this quantity is, and here is, I have done that. So I am plotting ground state energy as a function of G. So this is our H is equal to 0 point, and it starts at -1, as we know, and then it sort of goes nicely without any problem. So you are already a little puzzled. This looks, well, it looks nice and smooth. So what is there? What is, it doesn't seem to have any non-analyticity or anything like that. It looks very nice. Okay. All right, so it's not very encouraging, but let's continue on. Now what I can do is I can try to compute what is the expectation value of X operators on neighboring sites. What do I expect this to be? Answer, what is the expectation value of this? So when H is equal to 0, which is little g equal to 0, I should find that it is 1, because that's like the ferromagnetic state. And indeed, I do find it is 1. Okay. There is more. I can find out what is the fluctuation of this quantity. And I know that fluctuation of that should be 0, because I am in the ferromagnetic state. And indeed, that is 0. Okay. What happens when I go towards the paramagnetic side? What happens when I run when G goes to very large values? Then I know that this quantity should go to 0, right, which it does. Not only should it go to 0, its fluctuation must become as big as allowed, and that's exactly what's happening. So the fluctuation of this is going to 1. Okay. We can also look at other quantities. Remember the density of what we used to call as X-flip excitations, which in our new notation should be called Z-flip excitations. So we know that when I go G large, the Z quantity should go to 1. And indeed, you will see that the Z goes to 1. And if you look at what happens to expectation value of Z in the ferromagnetic side, expectation value of Z is 0, precisely as expected. Okay. Now we will also see something else. So remember, instead of Z, we could define this number of Z flip excitations, which is actually 1 minus Z by 2. Remember that? I could compute the fluctuations of those, right? So I can compute this delta Ni Nzi. That's the thing that we had defined using X operators in the previous notation. And you remember that at the ferromagnetic side, it becomes half, which is the maximum possible allowed fluctuation in the system. So you see that result is also recovered here. And it sort of comes down and it goes all the way to 0 again, precisely as expected. So all the results are as expected. But we know from duality something has to happen. We were expecting a phase transition. This looks pretty nice. if I look at some of these curves, you see that there's something funny happening near 1, there is something funny happening near 1 and something funny happening, there is something like an inflection point or some sort of thing is going on here. So maybe I should do something else to see whether these are, there is some phase transition of some kind. Okay. So before I discuss the phase transition and the nature of the phase transition, etc., I did not tell you how I computed this quantities by knowing the ground state energy. So I do not want to rob you of the pleasure of discovering that. So I invite you to do this. Okay, it's a very nice exercise for you to figure out how you can compute these expectation values just by knowing this ground state energy. Okay. So now we have to reveal the critical point, the main point of the discussion, as well as the critical point of the phase transition. Okay. So here is the message. So if I take the second derivative of the ground state energy, now I see that at G is equal to 1, the second derivative of the ground state energy diverges. And this is exactly signaling a non-analyticity of the ground state energy as a function of G. So the point G equal to 1 is a point where it is not analytic. Okay. So the value of GC, the critical value, is 1, and that if you put back dimensions, it tells you that HC is same as J, that is, I am fixing J and running H, and that exactly matches the result from duality. So remember, it's a self-dual point when H is equal to J. So we now have confirmed by an exact calculation that the point H is equal to J is indeed a point of non-analyticity of the ground state energy, and therefore corresponds to some kind of phase transition. Okay. So you can work out more details of this. I invite you to do this. It's actually very straightforward because you have the explicit form using elliptic functions. You can use the mathematics of elliptic functions, perform various expansions, etc. And you will be able to see that if you define something like a distance to transition, little t, this is conventional in statistical mechanics. So what I am going to do is I am going to define it as G minus GC by GC. In this context, it is just G minus 1 by 1. So it is just G minus 1. You can show that this divergence of the second derivative of the ground state energy with respect to G is a logarithmic divergence. You can actually show that. And this corresponds to a critical exponent alpha of 0. Okay, now I am taking derivative with respect to this parameter G. Now after some study, you will see that this is effectively taking some second derivative with respect to a variable corresponding to the distance to the transition. So in the standard Ising model, classical Ising model, that would be temperature. So this is actually, this will turn out to be like the specific heat divergence. Okay, I will have more to say about this in the coming slides. Okay, so what have we established so far? Simply by finding the ground state energy, we have seen that a variety of observables that we had studied before have similar and expected properties as what we found from perturbation theory as well as our physical intuition. We have found that there is some kind of non-analyticity at G equal to 1, and we call that the critical point. So let's explore what is happening near the critical point. So to see this, what I do is I plot the dispersion, the energy E of this gamma particles as a function of T. So this result is for T equal to minus 0.2, and you see that the dispersion has a gap. there is a gap in the excitation. There is no value of k at which the excitation has zero energy. And remember, this whole thing is now done in the thermodynamic limit, and if you go back to the definition of gap, the gap is you find the excitation at any finite system size and then run the smallest value of excitation energy and take the limit as thermodynamic limit, namely n going to infinity, and you will find that there is a finite gap. So this is true when t is positive, t is negative here, and also when t is positive. Now watch what happens when t is equal to 0. When t is equal to 0, the gap vanishes, and in fact at crystal momentum k equal to 0, the gap is the E of k is exactly 0 when little t goes to 0, namely G is equal to G critical. In fact, you can plot this gap as a function of t, and I have obtained this analytically. You can get it from the dispersion that we have, and you will see that it vanishes. And so our main point is that the critical point, namely G equal to Gc, the system becomes gapless. There are gapless excitations at the critical point. At any other point in the phase diagram of the transverse field Ising model, the system is gapped. At the critical point, the system becomes gapless. You can actually study the gap as a function of the distance to the transition, and you will find that it goes in the it depends on the distance to transition in this fashion. Okay. So I have written this in dimensionless language. So this must be thought of as delta by the physical gap by j, so that it becomes a dimensionless number. So that's what this delta by j is. This is written already as delta by j. So that goes as 2t, and now you see that the gap vanishes as a power of t, and that power here is unity, and that number, the power here, is called the dynamical critical exponent of this transition. Okay, it's called the dynamical critical exponent, and typically it's called z. So this theory has z is equal to 1. So remember, energy is related to somehow inverse time, right? So what this is telling you is that space and time are on equal footing in this transition, right? I'll have more to say about this in the next slide. So you see that this is what is happening at the critical point. So the main message of this slide is that at the critical point you have a vanishing gap, or the system is gapless at the critical point. Away from the critical point, you generate a gap in the system. The system is gapped, and the way the gap closes as we approach the transition is characterized by an exponent, and that is called the critical dynamical critical exponent, and in this case that critical exponent turns out to be z is equal to 1. Okay, let's explore a bit more further. So now imagine that I try to find the low energy physics. What do I mean by low energy physics? So suppose all my excitations are gapped, say. So let's say that let's go here. For example, here the gap will be something like 0.4. So this 0.4 is in some units of j. So imagine j were some humongous scale, some 10 to the 20 eV or something like this. Then small energies that you have will not be able to excite anything here. So as I come closer to the critical point, that the gap energy state scale will start coming down, and I could sort of try to excite things near the k equal to 0 point. So the question I am asking is, what theory can I write down if I focus near k equal to 0? So I am looking at k's which are much smaller than pi. So this corresponds to long wavelengths of excitations. Remember, k is like inverse wavelength, and if k is going to 0, it means the wavelengths are going large compared to the lattice spacing. And now I look at what is the effective Hamiltonian of such small momentum particles. So now it's just a matter of doing some algebra. So when k is small, I can write cos k as 1 minus k square by 2, and it has no linear term in k, and sin k is just k for small k. So to linear terms in momentum, this term looks like g minus 1, which is t, remember, and minus t here, and then this is just ik minus ik and ik, and you see this. So now you see something absolutely spectacular. If you now Fourier transform these ck and c minus k using momenta which are small, the inverse Fourier transform can be thought of as some kind of field, fermionic field, which we call little psi k, and this whole theory can now be written in this fashion, right? So what is this? This is some psi dagger. So remember, this capital psi is like a spinner, if you wish, a two component object with psi and psi dagger, and this psi dagger is simply the transpose conjugate of this field. So now if you think about this, these are fermionic operators. The dagger operator is not independent of this operator, because you see these have already components psi and psi dagger here. And these are Pauli matrices, and if you study this, this looks like the Dirac equation. It would have been the Dirac equation if this psi and this entry here were independent objects, but now they are not independent objects. And this is actually a theory of Majorana fermions. So this is a Lorentz invariant theory. So this theory, if you work out what are the symmetries of this theory, the theory is symmetric under Lorentz transformations. So you can transform space and time using some speed of light, which is like the slope of this, there is a slope for the linear dispersion here. If you use that as the speed of light, you will find that this theory is invariant under the Lorentz transformation of that. So what do you learn from this? You learn something spectacular and mind-blowing, which is that near the critical point, I have an emergent symmetry in my system. Remember, I started off with a lattice which knows nothing about Lorentz invariance and all that. I just have a bunch of sites, and there are particles that are hopping on that site and so on. That's basically what I have. Or if I think in terms of qubits, I had a bunch of qubits which were interacting with each other. And what is happening is I tune the parameters of the theory. I reach point of Gapless point, and at that point, and in fact in and around that point, I have an low energy theory which has an emergent symmetry. Remember, the symmetry is not true at all scales. It is a low energy, it's an infrared symmetry. That's why we use the word infrared. And this effective theory at low energies has an emergent symmetry. So if you are, remember our view of the transverse field Ising model as a universe, a toy universe. So if you are a person living in this toy universe, you might imagine a world where on the scales that you are probing, remember on the scales of your experiment, which is just around this region, you will conclude that the universe that you are living has Lorentz invariance, and that the symmetries of the world are described by Lorentz transformations and so on. Whereas, if somebody had a lot of energy, there are bazillions and bazillions and of electron volts of energy, they could probe other things and they will find that the universe is not Lorentz invariance on that scale. For example, this one turns around like this, right? So the main point is that low energy symmetries can be emergent in the system. This is a big lesson coming out of the transverse field Ising. There is something more. there is this T term which is the distance to the transition, and you can see that acts like the mass of these Majorana fermions. Okay. So you will see that as if a fermion has a mass, then it also has an associated wavelength, Compton wavelength, or another way of saying it is there is a length scale associated with that. So if T is the mass, then inverse of that is related to the some length scale, and therefore you will now see that this tells us that there is an emergent length scale in the problem near the critical point, and that diverges as T inverse. And I am able to say that the length scale is inverse T simply from this idea that this theory has Lorentz invariance, and if I have a particle of mass m, then associated with that there is this length scale. So this exponent is called the exponent nu. It tells you that the emergent scale diverges as T to the power minus 1. Remember, such an emergent scale also showed up when we discussed the one-dimensional classical Ising model, and that length scale also diverged as I went to 0 temperature. Here this length scale also diverges as I approach the critical point, and it diverges in a characteristic way characterized by the exponent nu, and for this problem nu is 1. Okay. So this is what is happening in the vicinity of the critical point. We can also ask what is happening at the critical point where the mass goes to 0. At the critical point, the theory is described by massless Majorana fermions. So that is the theory. Okay. The characteristic length scale has diverged, and there is no other length scale remaining in the problem. So what does this mean? This means that if you look at any kind of correlation functions, for example, I have computed here the correlation function between z at site I and z at site j, you will see that this correlation function does not have any intrinsic length scale in it, and we will see this what this means as scale invariant later in the course, but for now we will just use this as a term. It will turn out that the system has no intrinsic scale and becomes scale invariant, and the correlation functions become power laws. For example, this quantity which I mentioned zi zj, it will go at large separations between I and j being much greater than 1. It will go as 1 by I minus j square. I have done this calculation using the exact solution. Okay, I am not revealing how I did that calculation, and of course, if I do that, I will be robbing you of the opportunity to discover this yourself. So please go ahead and do that. But I have plotted the results of my calculation here, and you will see that this calculation exactly produces this 1 by distance square. How do I see that? You see, this is 2 decades of length, and this is about 4 decades of this quantity. So you can see that it's going as square of that. So this is also an extremely revealing piece of information. It has taught me that at the critical point, I don't have any intrinsic length scale or some emergent length scale that is remaining. The length scale is diverged, so it has nothing to say about, it doesn't determine any other distance, and my correlation functions start to become power laws at the critical point. Okay, if you go away from the critical point, you will see that these such correlation functions will die exponentially, and it will die exponentially with that scale which we had discussed, the C scale. Okay, so it's time to have some perspective. So we have found many new things. So we should see where does this sit in the bigger picture. So it's important to get this perspective. So first thing is, I showed you a small collection of results, and I chose those collections of results which are easy to obtain from the solution which we have done, which we have shown in this lecture. You can compute other things which are a little bit more involved. So I am not showing you those calculations, but I am just quoting the result here. So for example, if you remember way back in our first lecture or so, we showed that the magnetization below Tc will start to grow with some exponent, and that is called beta, and you can show by a calculation, it has been done by many people, that beta here is 1 by 8. It is a bit of an involved calculation, but okay, you could try it at some point. Alright, so what we have done is we have studied the problem by mapping the ground state of the 1D TFIM to fermions. So how can I use these results in a broader setting? Recall that the ground state of this D quantum system corresponds to the thermodynamic limit of the D plus 1 dimensional some classical problem. But we know that the classical problem corresponding to TFIM is the two-dimensional classical Ising model. So what I want to point out to you is that what we have done by finding the ground state of the TFIM is that the critical point that we have discovered here and the critical properties around that critical point are same as the critical properties of the two-dimensional classical Ising model. So we have actually quote unquote solved the two-dimensional classical Ising model exactly, in a sense, right? And we have extracted certain critical exponents which are easy to extract, at least at the level of calculations that we have done. And as I comment here in a caveat, you can, it's not really a caveat, it's just piece of information. You can compute all the critical exponents by more sort of detailed calculations using this approach. Okay friends, so it's a good time to summarize this chapter. So this has been a fairly long chapter. We have discussed quantum models in this chapter, and let's see what are the main things that, what are the take home message that we need to keep in mind. So one central thing that we discovered in study of quantum systems is that the d-dimensional quantum ground state, in the thermodynamic limit of that problem, will be some d plus 1 dimensional classical thermodynamic limit. Zero temperature of d quantum problem, if the d is greater than or equal to 1, then you have to also take thermodynamic limit in that other direction, will be a classical problem in its thermodynamic limit with different coupling constants. So this offers two types of opportunities. First is you can study quantum problems and their ground states to say something about classical phase transitions in one higher dimension. You could do the other way around as well. You can study classical problems and say something about quantum phase transitions in one lower dimension. So another very important thing is that if there are ways in which you can map problems from one kind of particles to another. So hardcore bosons can be mapped to fermions and so on. So that's an important piece of information. So from the perspective of our pursuit of understanding phases and phase transitions, what is it that we have learnt by solving the TFIM and studying Ising model per se? So first is of course this mapping idea that we can study ground states and extract critical exponents. And I cannot overemphasize this point. What we have seen is that at the critical point, you see that the system has a larger symmetry. So, for example, we started the ultraviolet, as it's called, the set of sites and qubits that we put in there. They had no Lorentz invariance and all of that stuff. But at the critical point, and in fact in and around the critical point, you see that the theory will become Lorentz invariant, the low energy theory. That is, effectively, if you view the system on large length and time scales, you will see, as you will experience Lorentz symmetry. The critical point itself has no scale remaining. The existing scale that the system had generated, the correlation length, has diverged. And what you end up having is a scale invariant state, and this is also an extremely important message that the study of the Ising model is sending us, and we must remember this. Okay friends, so we have concluded this chapter, and what we are going to do next is we are going to start looking at more complex systems, more complicated and more involved systems in higher dimensions, etc. And you will see that all these techniques of using series expansion, small parameters, etc. will not help us there in any serious way. So we have to look for other methods. So we are going to explore methods which are non-perturbative in nature, and I'm sure you will find those approaches also very exciting, and I'm looking forward to see you in the next lecture.